Hi, I'm Aaron Bostrom, and I'm from the University of East Anglia, and I worked on, I'm a second year PhD student, and I worked on my paper evaluating improvements to the ShapeletTransform with my supervisor, Anthony Bagnall, and my colleague, Jason Lines. Cool. So before we get started, just want to define what time series classification is. I know we're obviously at a time series workshop, but I think it's just good anyway. So given a set of instances of time series from 1 to n, each series has m ordered real valued observations and a class label. So ultimately what we're trying to do is to define the underlying pattern for each class in the series to predict the class label. So my area of research specifically is trying to improve the ShapeletTransform in terms of speed and accuracy. And so my presentation is into 4 sections. Firstly, I'm just going to give you a quick overview of the ShapeletTransform. I know I haven't got a lot of time. And then I'm going to talk about the 2 methods that I proposed in my paper on how we can improve the ShapeletTransform, and then conclusions and further work. So firstly, what are shapelets? So time series shapelets are a data mining primitive that were first introduced in 2009 by Yi and Keogh. And then they provide a mechanism for measuring local similarity between series by observing common subsequences. And this original research embedded the shapelets in a decision tree using them as rules. And then in 2012, my research group proposed the ShapeletTransform, which was significantly better than the shapelet tree, where we take the shapelets out of the decision tree and use them as a data transformation process, and then we can use them on regular classification algorithms. So I'm going to quickly define a shapelet. This is the gunpoint data set as well. And so given a series TI, which is 1 to m and its class label, a candidate shapelet is any common subsequence, any subsequence in T of I. And a good shapelet is what we would say is maximally indicative of class membership. So we have class 1 and 2, which are the long series, and if you can see the little orange squiggle is the best shapelet that we find when we run the Shapelet algorithm. And it's pretty obvious why it's able to differentiate between the blue series and the orange series. So this is the Shapelet algorithm in its kind of simplest form. And there's been many improvements to the Shapelet transformation in the last couple of years, but for simplicity, I've kept it quite light on how it works. So I'm just going to run through it quickly before I get onto my improvements. So we have our set of instances, which is T, and we have these min and max parameters, where you can set the minimum or the maximum length that a subsequence can be within that series. And there has been some work around kind of optimizing those 2 minimum max parameters to kind of reduce the set of possible shapelets that exist. But for the most part, actually, we found just setting the minimum to 3 and the maximum to m, so the entire series, where you're looking at the entire problem space, is actually the best way to do this. So we've got these are our input parameters, and then the k value, where rather than before in the shapelet tree, they were looking for 1 shapelet, that's your rule, split, and then recurse. We have this k parameter, which is how many shapelets that we're looking for, and we want our k best. So we also found that actually having just lots of shapelets and then transforming on our data and letting traditional classifiers deal with redundant attributes was a good way. So actually we set k to between n and 10n. So sometimes we'll look for 1,000 or 2,000 shapelets within a set of instances. So running through, we set our set of shapelets to empty, and then for every time series, we need to generate a set of shapelets between those min and max in this generate candidates function. And then for each shapelet candidate that we've generated, and bearing in mind, in that generate candidates function, for a full brute force, there is nm squared shapelets. So it gets really big, really fast. And then we need to evaluate each shapelet to see how effective it is at differentiating between the classes. So we calculate a set of distances where we compare each singular shapelet to every other time series through a sliding window function, finding its best fit in place. And then using those set of distances, we can calculate the entropy and the information gain to see how good of a splitting rule, how good of a rule it is, or how good of a shapelet it is. And then coming back up, with our sets of shapelets, we sort them by quality and then remove the self-similar, which is the overlapping shapelets, because often there's a lot of redundant information, and then we merge them all back in to give our number of shapelets. So once we've got our set of shapelets, we do the data transformation. So given k shapelets, we transform each instance in our training and test data by that set of shapelets, where we then generate a new matrix of information, a new matrix of data, which is k by n. So for each series, you calculate this distance to each shapelet, transforming as you go. And then because we have a set of data that's no longer temporally ordered, we can use any classification algorithm we like on it. And so that's the Shapelet Framework. Since I started my PhD about 2 years ago, I spent quite a lot of time working on the Shapelet algorithm, and part of our work is developing an open source Weka time series framework, which is an extension of their framework. And so because there's been a number of heuristic techniques proposed, I wanted to develop a framework that you could build the Shapelet algorithm and mix and match and pick any optimization techniques that have been proposed, turn them on and off, and really thoroughly test them, especially with these being heuristics. It's often quite difficult with the large amount of data sets that we have to know how effective they can be on their own and in combination. So we needed a good test suite to be able to understand whether our work was good or not. So some of the ones that we've got are different distance measures where they've different early abandons, different encodings for class values, different quality functions, and different search techniques as well. So not necessarily a brute force search. And that nicely brings us on to the operation count. So with our Shapelet framework and our defined ability to test and turn on off these heuristics, we need a way to objectively measure their ability to reduce their work, or reduce the work of the brute force, or reduce the work of the ShapeletTransform. So at the lowest level, or the fundamental operation of the Shapelet algorithm, is that Euclidean distance function where you're comparing time series segments. And this is the order n squared at m to the 4. And so simply, we just count the number of addition operations in that distance function. And that gives us a good way of seeing how much work we can avoid when we do different optimizations. So the brute force with no optimizations obviously does 100% of the work. And so the first method that I proposed was FastShapelets. The first method that I'm going to talk about is FastShapelets, which was proposed in 2013. And that was an adaptation of the Shapelet tree algorithm, where they use symbolic aggregate approximation to smooth and shorten these series and discretize them. And then using random projection, they use a hashing function to build these histograms to kind of find these common subsequences or common words that exist. And that enables them to efficiently kind of prune the search space of possible shapelets, so that when you are doing the quality assessment of a shapelet, you don't have to do as much work. So I like to think of FastShapelets as an improved search function on how to kind of find shapelets rather than, So obviously my research group proposed the ShapeletTransform as an improvement to the Shapelet tree. So I'm saying, can we do the FastShapelets as a transform, and does that significantly improve its accuracy by taking it out of that decision tree classification model? So, and also it worked quite nicely as proving that we could have different search functions in my Shapelet framework. So I'm going to talk about the results now of how that went. And I'm going to talk about two results really, which is speed and accuracy. When you're doing heuristics, you can maybe justify a slight loss in accuracy if you have a significant gain in runtime. So when we compare multiple approaches, we use critical difference diagram. And for comparing two classifiers, I've used the Wilcoxon sign rank test. So this is the operations counts data where we're measuring the amount of work across. This is done across 52 data sets where we do a significant amount of resampling to kind of increase the amount of problems that we have. And that gives us, I think, around about 8,000 experiments approximately to test the success of this heuristic. So as you can see, blue is worst, orange is the averaged kind of percentage of operations avoided, and then the gray is best, which you can't actually see on the final one because it's so small. But basically, I tried the FastShapeletsTransform as a search on its own, no other optimizations. I then turned on our searches with just a brute force, and then I combined them, the two. And you see, I think, in the best case, we avoid, I think it's 99.999% of the work. It's about 10 to the, I think it was about 10 to the 5 operations out of 10 to the 12. So it was massive. It was ridiculous. But you can see that they both, that the amount of work reduced is quite significant. So moving on, this is a quick table of results. I'm not going to spend too long here, but I just want to, so this is the table, and yeah, there's about 5,000 or 6,000 experiments that have gone on to produce these averaged accuracies over the data. And so the key thing really that stands out is the FastShapeletsTransform, whilst being significantly faster than the ShapeletTransform, isn't more accurate than the ShapeletTransform. But when we compare the FastShapeletsTransform to FastShapelets, everything above the orange line is FastShapeletsTransform is better. Everything below is FastShapelets is better. And so I think it's 36 out of those 52 resampled data sets, we see that the FastShapeletsTransform is better. And then when we did a Wilcoxon sign rank test comparing the FastShapeletsTransform and the FastShapelets, that was there was a significant difference. In the critical difference diagram, I've compared it to ShapeletTransform, 1N CV DTW, FastShapeletsTransform, and FastShapelets and a rotation forest. So those are just general benchmarks. And the cliques within a critical difference tend to be conservative of the significant difference. So FastShapeletsTransform was good, but it didn't really do what we wanted it to do, and that's dealing with this massive time complexity. So we researched and evaluated, lots of optimizations, but often lots of these are very complex, and and whilst they do work on some of the really massive data sets in the UCR repository, some of them have time complexity in the order of 65,000 days. So they're probably going to not run if I set them going in my lifetime, to kind of put it into perspective. So before I continued sort of researching different search techniques and different distance optimizations and all this kind of stuff, I wanted to see if we could just simply sample the data. Are the shapelets robust to just smaller data set sizes, despite the fact that we have loads of data? And so that's what we did. But I also wanted to calculate how long a data set would take to run. And I also wanted to build a contract classifier where I could set a specific amount of time for the ShapeletTransform and then say run for this and do as much as you can. But I wanted it to be a bit clever. So I defined the time complexity, I solved the time complexity, and then through rearranging the time complexity, you can then calculate a new size of data set that will work with this with a bounded time parameter. And so we use the sampling process that maintains the original distribution, and there's a lower bound on that sampling process, so that we have to always have at least 25 of the least represented class. Otherwise, you could sample it down and have one of the least represented class, and you probably learn not a lot. So if you have, with this lower bounding on the least represented class, you need a way to deal with what happens if you kind of overrun or if you need to sample more because because your time is running out. So we also define a really simple skipping parameter where I don't consider every position and length of Shapelet, and through the definition of the runtime complexity, I can actually calculate ahead of time what my skipping parameters be, what my dynamic sampling should be, so that I can run within a day, which is pretty useful on a data set that takes 65,000 days. So this is just a simple algorithmic description of how we dynamically sample. It's pretty straightforward, where Q and P are the skipping parameters, and then that is what I've defined as the factory transform, where we dynamically sample given a time threshold and do some skipping, do some sampling, and also pick some of the heuristic methods that we want and the appropriate components, really. So just quick results. The left column, which is kind of cut off, is the factory transform. The one in is the Shapelet transform. And so I can't remember off the top of my head now how many we win on. Can I see on here? The factory transform. So that was on 42 data sets, and we win 32 times out of 42. So everything above the orange line is the factory transform is better, and everything below is the Shapelet transform is better. So moving on. So we found the factory transform was significantly better than the Shapelet transform when compared on 42 problems we threshold to 1 day. Those are also run on the 85 UCR problems and with 100 resampling. And so I ran about 4,200 experiments. The reason I haven't done the whole 85 is because 43 of them are less than a day to brute force. So that's obvious. One interesting thing before I finish is only 11 of the data sets actually required any skipping parameters over 4. So most of them, with just a little bit of sampling, meant that they could be run in a day, which is really handy. So finishing up, the downside to using Shapelets is time complexity, and our aim was to speed up the original. The FastShapelets was okay, but I think with a little bit more work, we could maybe make it slightly a bit better. And the dynamic sampling, I think, has fulfilled what I wanted it to do. The very longest problems, where we have significant amounts of sampling, weren't as accurate as they could be, and I think there needs to be a bit of work there. So other work that I've been looking at is other heuristic searches. I tried completely random shapelets, so just keep finding random shapelets in the whole set until you run out of time. And that was okay. And I've also been looking at hill climbers and simulated annealing for kind of looking at that search space and finding them with avoiding brute force. And that's working-ish, and needs a bit of work. And then we're also looking at multivariate shapelets and what that means. So, cool. I'm worried for time.
All right, thanks. Hey, thanks for the talk. Could you briefly discuss about what's the difference if we use wavelet-based coefficients as features for classification versus this approach? Is it an accuracy? Is it an complexity?
What was the question, sorry?
So if I transform the time series into wavelets,
yeah.
Let's say at a fixed level, and then use those as features for classification,
yeah.
Versus using shapelets or faster shapelets that you mentioned, can you briefly discuss about what am I going to gain, what am I going to lose?
What, by doing the transformation?
Yes.
So by doing the data transformation, you and moving away from the shapelet tree, you gain a lot more flexibility in the choice of classifier that you have available. So actually, we use whenever we do our classification on our transform, we use an ensemble technique called HESCA, or we've called it the weighted ensemble before, and that actually means that you can use rather than embedding it in just one tree, you have multiple classifiers available. Is that? Have I misunderstood your question?
Do I have time? Or? Yeah, so no, I was talking about instead of using shapelets, I just use wavelets. right? And if I use those coefficients for classification
Okay, yeah,
as
sure.
features, what would I gain, what would I lose? In the sense, would I gain accuracy, would I lose in computation time, or?
I've never, I don't know if I understand your question.
Probably I'll ask you later.
Yeah, that's probably a good idea, yeah.
Any other question?
So it seems like learning or finding these shapelets is a means of getting a good representation of the data.
Yeah.
So why carry out this really elaborate search process rather than, say, learn the shapelets end to end?
Okay, so there is an example of learned shapelets within the literature by a guy called Joseph Graboka. I don't know if I presume that you've probably read his work. And so one of the fundamental differences between his work and ours is the shapelets that he finds through a kind of linear regression is don't or might not, for the most part, don't exist within the original data set. And so you lose some of the ability to kind of to discern what the shapelets mean. So if you get your set of shapelets back, you can, like I did with that data set there, at the beginning with the gunpoint data set, I projected that shapelet that we found back onto the data set. And it's immediately obvious why it's a differentiating feature between those two classes. Whereas, and it's a real world thing that exists. Whereas with the shapelets that are learned and generated, when you put them back onto the series, you may not be able to, as a human, be able to kind of appreciate what kind of information it's conveying to you. Does that answer your question?
That answers it.
Cool.
Thank you very much. Let's thank the speaker one more time.